Welcome everyone to this live podcast on Twitch, where you can find the news from the research industry that how our researchers keep on researching on various topics and domains to keep our lifestyle better, of course. And these articles are posted on our website named postscientist.com. If you are willing to check it out, please check it out. Otherwise, listening to this podcast will be enough for you guys, as it acts like an archive on the daily basis, providing you the news from the research industry. So let's get started without wasting any further time. Yep. The first topic of the day is researchers resolve decades long debate about shock compressed silicon with unprecedented detail. Hmm. Silicon, an element abducted in Earth crust, is currently the most widely used semiconductor material and is important in fields like engineering, geophysics, and plasma physics. But despite decades of studies, how the material transforms when hit with powerful shock waves has been a topic of long standing debate. One might assume that because we have already studied silicon in so many ways, there is nothing left to discover. Okay, said Sylvia Pandolfi, a researcher at the Department of Energy SLAC, National A- Accelerator Laboratory. But there are still some important aspects of its behavior that are not clear. Now, researchers at SLAC have finally put this controversy to rest, providing the first direct high fidelity view of how a single silicon crystal deforms during shock compression on nanosecond timescales. To do so, they studied the crystal with X rays from SLAC's Line Coherent Light Source (LCLS) X-ray laser. The team published their result in Nature Communication on September 21st. What they learned could led to more accurate models to better predict what will happen to certain material in extreme conditions. This is a great example of an experiment that unnecessary to better understand certain materials, said SLAC scientist Adenia Glinson, who was the principal investigator. You have to start simple with a single crystal to know what you are tracking and understand it in really detailed way before you can build up complexity to give way to say the next semiconductor of the 21st century that will allow the electronic industry to continue the remarkable progress seen in the past 50 years. Time to relax. When researchers shock compress samples, they are essentially sequencing the material along one direction. This creates so much stress is that single direction that the material needs to find a way to relax. In many materials, this normally leads to plasticity and irreversible deformation driven by the generation and diffusion of effects. Tiny imperfection in the material atomic arrangement. In earlier studies, researchers interpreted the different features seen in shock compressed silicon as a signature of the plastic deformation, but molecular simulation suggested a different defect free deformation. In our experiment, we showed that in the case of silicon, this conventional plasticity is not the main relaxation mechanism, said Pandolfi, who led the analysis. Rather than the accumulation of defects, silicon prefers to relax through the collective motion of its atoms and transformation into a high pressure structure. This had been predicted by calculation, but until now was very difficult to prove experimentally, apples to apples. At the matter in extreme condition MEC instrument at LCLS, the researcher first sent a shock wave through the silicon sample with a carefully tuned optical laser, allowing them to reach extremely high temperature and pressures. Next, they hit the sample with ultra-fast X-ray lasers, pulses from LCLS. Some of the X-rays then scattered into a detector, allowing the researcher to observe how the sample atoms rearrange in response to the increase of pressure and temperature during the shock wave propagation on ultra-small, ultra-fast scales. Previous studies focused on bulk response in sample consisting of many small crystals in different orientations. This allowed researchers to determine the average behavior of the material, but did not allow them to get the complete picture. Working with a single crystal sample allowed the researcher to follow up how the crystal transformed at the atomic level. The success of the experiment was due to incredible combination of sample quality and the X-rays from LCLS. Pandolfi said, were able to access the fundamental materials science without having to factor in distortion due to X-ray source or microstructure defect in the sample that could change how the material behaves. It much more of an apples to apple comparison with the theory. It allowed us to visualize what happened in what is as close as possible to a model system. Springboard technique. The ability to gain atmospheric insight into how material responds to stress is informing the design of next generation of X-ray facility. The matter in extreme condition upgrade MECU will produce unprecedented pressure combined with higher energy X-ray to probe a much wider array of conditions, enabling complex systems of direct relevance or to future technologies to be studied. Example range from the semiconductor industry to fusion energy and the protection of satellites. We are looking at this as a springboard technique development. Glinson said it can be leveraged for many different applications beyond silicon, really pushing the frontier for new material and helping us to eliminate the path toward engineering these materials to benefit humanity. Getting the physics right. To follow up on this study, the researcher planned to try this technique on different samples with more complex composition to better understand foundational materials relevant in industry as well as earth and planetary sciences. This new data really shows where the plasticity model that are used to predict how material will behave are getting the physics right and where we need to make changes. Glenson said, there are other materials that respond in a similar way that are often used for industrial purpose. For instance, high performance coatings to withstand extreme conditions such as micro meteorite impacts on space vehicles. Understanding how these materials degrade over time in this environment will help us figure out how to prevent that in the future. It all starts with having accurate atomic level models. The researcher plan to conduct more silicon experiments to see what happens when they compress the sample along different orientation and figure out if over they apply the strain changes how the sample deforms. For Pandolfi, the possibility of uncovering more unknowns about these ubiquitous and useful elements is one of the most exciting aspects. I have such a soft spot for silicon. Anything new I can discover about it is so interesting to me. Pandolfi said, sometimes I have to stop and think about what we are talking about. We are looking at the motion of atoms at high pressure over the course of billions of a second. The fact that we can get such clear information on a phenomena that people have been investigating for such a long time is just mind blowing. I mean, there is no need of any explanation by my side, of course, as it already described by the author very well. So, yep, moving towards next topic. NASA Chandra finds a galaxy cluster collision on a whim. Okay, let's see. Astronomers taking inventory of the material in the local universe, local universe keep coming up short. A new result from the NASA Chandra X-ray Observatory about a system of colliding galaxy clusters may help explain this shortfall. Although scientists know a great deal about the composition of the universe, there has been a vexing problem they have struggled to explain. There is a significant amount of matter that has not yet been accounted for. This missing mass is not the invisible dark matter, which makes up a majority of the matter in the universe. This is a separate puzzle, where about a third of the normal matter that was created in the first billion year or so after the Big Bang has yet to be detected by observation of the local universe that is in region less than a few billion light years from Earth. This matter is made up of hydrogen, helium, and other elements and makes up objects like stars, planets, and humans. Scientists have proposed that at least some of this missing mass could be hidden in gigantic strands or filaments of warm to hot temperature of 10,000 to 10 million kelvins gas in the space in between galaxy and cluster of galaxies. They have dubbed this as the warm hot intergalactic medium or WIM. A team of astronomers using Chandra to observe a system of colliding galaxy clusters has likely found evidence of this whim residing in the space between them. Finding this element of missing matter has proven to exceptionally difficult and only a few samples are known, said Arnab Sarkar of the Center of Astrophysics, Harvard and Simpson CFA in Cambridge, Massachusetts, who lead this study. We are excited that we have likely pinpointed another. The researcher used Chandra to study Abel 98, which contains a colliding galaxy cluster about 1.4 billion light years from Earth. The Chandra data reveal a bridge of X-ray emission between the two of the colliding cluster containing gas at a temperature of about 20 million kelvins and cooler gas with a temperature of about 10 million kelvins. The hotter gas in the bridge is likely from gas in the two clusters overlapping with each other. The temperature and density of the cooler gas agree with prediction for the hottest and densest gas in the WIM. Hmm. In addition, the Chandra data shows the presence of a shock wave, which is similar in a sonic boom from a supersonic plane. The shock wave is driven by and located ahead of one of the galaxy cluster as it is starting to collide with another cluster. This is the first time astronomers have found such a shock waves in the early ages of galaxy cluster collision before the center of the cluster pass by one another. We think the shock wave is an important discovery because our model have predicted such a feature should be there, but we haven't seen one until now, said co-author Scott Randall, also of CFA. There is a key part of the early collision process that will eventually lead to a merger of the cluster. The shock wave may be directly connected to the discovery of the WIM in Abel 98 because it has heated the gas in between the cluster as they collide. This may be raised the temperature of the gas in the WIM filament estimated to contain some 100 billion times in the mass of the sun, high enough to be detected with Chandra's data. Galaxy cluster which contain thousands of galaxies, huge amount of hot gas, enormous reservoir of dark matter, are the largest structure in the universe held together by gravity. Scientists think they are able to reach their colossal size by merging with one another over millions or billions of years. When galaxy clusters collide, we get a chance to see extreme physics that we rarely see in any other cosmic setting. Of course, said Yunwan Su, a co-author from the University of Kentucky, a paper describing the result by Sarkar et al. Was published in the Astrophysical Journal Letters. I mean, it's a great finding. It's a great study, and of course, it's been seen and that how this universe is so much diverse, which we can't even imagine. So yeah, great. Moving on towards next topic. Hmm. Record-breaking gamma ray burst, possibly most powerful explosion ever recorded. Okay. In the early morning hours of today, 14 October 2022, astronomers using the Gemini South telescope in Chile, operated by NSF NORD's lab, observed the unprecedented aftermath of one of the most powerful explosions ever recorded, gamma ray burst GRB 2200 NA. This record shattering event, which was first detected on 9th October 2022 by orbiting X ray and gamma ray telescope, occurred 2.4 million light years from Earth, was likely triggered by a supernova explosion, giving birth to a black hole. A titanic cosmic explosion triggered a burst of activity from astronomers around the world as they raced to study the aftermath from what is one of the nearest possible, the most energetic gamma ray burst GRB ever observed. Just released observation by two independent teams using the Gemini South telescope in Chile, one of the twin telescopes of the International Gemini Observatory operated by NSF North Lab, target the bright glowing remains of the explosion, which likely herald a supernova giving birth to a black hole. The GRB, identified as GRB 2200 NA, occurred approximately 2.4 billionth light years away in the direction of the constellation Sagitta. It was first detected the morning of 9th October by X-ray and Gamma Ray Space Telescope, including NASA Fermi Gamma Ray Space Telescope, Neil Gehrels Swift observatory and wind spacecraft. As the word of this detection quickly spread, two teams of astronomers worked closely with staff at the Gemini South to obtain the earliest possible observation of the afterglow of its historic explosion. In the early morning hours of Friday, 14 October, two rapid target of opportunity imaging observation were conducted by two independent teams of observers led by graduate students Brendan O'Connor, University of Maryland, Washington University, and Gillian Reston Jad, Northwestern University. The observation occurred more minutes apart. The first observation used the Flamingo's instrument, a near-infrared imaging spectrograph. The other observation used the Gemini multi-object spectrograph, GMOS. The team now have access to both dataset for this analysis of the energetic and evolving event. The exceptional long GRB 2200 NA. For those who are not able to understand the GRB 2200 NA, which I am again talking about, it's a star name which is being identified or given any star in the universe to get into the database of the NASA or wherever the space organization really is. So I mean they are sharing those data with each other self. So it's being if it's being already been discovered by another scientist, then it's been recorded in the database as a number which I'm talking about, and this star number is GRB 2200 NA. So I mean astronomers already know it, astronomer scientists, astrophysics scientists, but for those who are not able to understand, I explain to those guys. Okay, because this burst is so bright and also nearby, we think there this is once in a century opportunity to address some of the most fundamental questions regarding this explosions, from the information of black holes to tests of dark matter models. Thanks to the fast reaction of observer and staff combined with the use of Gemini director, decisionary time and efficient data reduction software like Gemini Dragonfire fast initial reduction engine. This image was quickly produced soon after the observation. The agility and responsiveness of Gemini infrastructure and staff are hallmarks of our observatory and have made our telescope go to resources for astronomers studying transient events, said Gemini chief scientist Janice Lee. Already communication have gone out to fellow astronomers through the NASA Gamma Ray Coordinates Network, the archive of which is now filling up with reports from around the world. Astronomers think it represents the collapse of a star many times the mass of our Sun, which in turn launches an extremely powerful supernova and gives birth to a black hole 2.4 billion light years from Earth. In our research group, we have been referring to this burst as the boat or brightest of all time, because when you look at the thousands of burst gamma ray telescope have been detecting since the 1990s, this one stands apart, said Reston Jad. Gemini sensitivity and diverse instrument suite will help us to observe GRB 2200 NA optical counterparts at much later times than most ground-based telescope can observe. This will help us understand what made this gamma ray burst so uniquely bright and energetic. When black holes form, they drive powerful jets of particles that are accelerated to nearly the speed of light. These jets then pass throughout what remains of the progenitory star, emitting X-ray rays and gamma rays as the steam into space. If these jets are pointed in the general direction of Earth, they are observed as bright flashes of X-rays and gamma rays. Another gamma ray burst this bright may not appear for decades or even centuries, and the case is still evolving. Of note are another extraordinary report of disturbance in the Earth ionosphere affecting long wave radio transmission from the energetic radiation from the GRB 2200 NA event. Scientists are also wondering how very high energy 18 tera electron volt photons observed with the Chinese Large High Altitude Air Shower Observatory could defy our standard understanding of physics and survive their 2.4 billion year journey to Earth. This event, because of this relative proximity to Earth, is also a unique opportunity to better understand the origin of the elements' behavior than iron and whether they all come slowly from neutron star mergers or also from collapsing stars that triggered GRB. The Gemini observation will allow us to utilize this nearby event to the fullest and seek out the signature of heavy elements formed and injected in the massive star collapse, said O'Connor. Hmm. So, it's being identified or being predicted by our scientists because, according to the database, by the 1990s and till the 2021, it's being identified that these gamma rays being either be either be the neutron star mergers or collapsing star that trigger the GRB. So, these are the discovery given by our scientists, NASA scientists, of course. So, yep. Moving on to our next topic. Hamilton of exceptional points from various degeneration points observed for the first time. Okay, let's see. A team of researchers from the University of Warsaw in Poland, the Institute Pascal CNRS in France, the Military University of Technology in Poland, and the British University of Southampton has shown that it's possible to control the so-called exceptional points. For the first time, physicists also observed the Hamilton of the exceptional points from different degeneracy points. You can read about the discovery that may contribute to the creation of modern optical devices. In the latest Nature communication, the universe around us is made of elementary particles, most of which have their antiparticles. When a particle and an antiparticle, that is matter and antimatter, meet each other, Hamilton occurs. Physicists have long been able to produce quasi-particles and quasi-particles, elementary excitations, charge, vibration energy trapped in matter, most often in crystal or liquids. The world of quasi-particles can be very complicated, although paradoxically, the quasi-particles themselves helps simplify the description of quantum phenomena, explains Jacques Skutschko from the Faculty of Physics at the University of Warsaw. Without quasi-particles, it would be difficult to understand the operation of transistors, light-emitting diodes, superconductors, and some quantum computers. Even abstract mathematical concepts can become quasi-particles as long as they can be implemented in physical systems. One of such abstract concepts are exceptional points. Theorists from the University Pascal, CNRS, in France, Guillaume Malpiuk, and Dmitry Slonchio explain the so-called exceptional points are specific system parameters leading to the communality of two different solutions that can only exist in systems with losses, that is, those in which the oscillations slowly fade over time, says Malpiuk. They allow the creation of efficient sensors, single mode lasers, or unidirectional transport. What is important? Each exceptional point has non-zero topological charge, a certain mathematical feature that describe the fundamental geometric properties and allow you to determine which exceptional point will be the antiparticle for another exceptional point. Adds Slunshoff, scientist from the University of Warsaw and the Military University of Technology, in the cooperation with the researcher from the CNRS and the University of Southampton, analyze the optical resonator filled with the liquid crystal. Liquid crystal are a special phase of matter in which certain directions are distinguished despite its liquid form. It can be observed, for example, by a light beam which behaves differently depending on the direction of incidence in relation to the optical axis of the liquid crystal. This feature, combined with the easy tunability by an external electric field, is the basis for the operation of common liquid crystal display. Polarized light, that is a special direction of vibration of the electric field of an electromagnetic wave, perfectly senses the direction of optical axis, and these are related to the direction of the elongated molecules of the liquid crystal. In the conductor research, the liquid crystal layer was placed between two flat mirrors, explained Victor Pensek from the Military Institute of Technology in Warsaw. The whole structure creates an optical cavity through which only light with a specific wavelength can pass. This condition is met for the so-called cavity resonance modes, that is light with a certain colored energy, polarization, and the direction of propagation. This corresponds to a situation where a photon that falls into the cavity can bounce multiple times between the two mirrors. The presence of a liquid crystal, the orientation of which can be changed by applying a voltage, allows the energy of the cavity modes to be tuned. In addition, the resonance condition changes when the light is incident at an angle, which in particular can lead different cavity modes to intersect with each other, that is, having the same energy despite different polarization of the light. For the specific orientation of the liquid crystal considered in the article, the two different cavity modes only for the four specific incidence angles of light when considering in an ideal structure without any losses. In fact, the light trapped within the cavity can escape through imperfect mirrors or can be scattered. The average time the photon remains inside the microcavity can be determined on the basis of a spectroscopic measurement. Moreover, due to the orientation of the liquid crystal layer, a difference was observed in the scattering of light polarized along and perpendicular to the axis of the liquid crystal. As a result, at the place of each degeneracy point for an idealized lossless cavity, a pair of so-called exceptional points were observed for which both the energy and lifetime of the photon in the cavity are the same. Matthew Scroll, who is the first author of the publication, described the experiment in the test system. It was observed that the position of exceptional points can be controlled by changing the voltage applied to the cavity. First of all, as the electric bias is reduced, the exceptional points created from different degeneracy points get closer to each other, and for a suitably low voltage, they overlap. As the approaching points have an opposite topological charge, they annihilate at the time of the encounter, so they disappear, leaving no exceptional points. This type of topological singularity behavior, that is the annihilation of exceptional points or from the different degeneracy points, has been observed for the first time. Earlier work showed the annihilation of exceptional points, but they appeared and disappeared at exactly the same degeneracy points, adds Ismail September, a PhD student at the CNRS. Exceptional points have been intensively studied in many different areas of physics in recent years. A discovery will allow the creation of optical devices whose topological properties can be controlled by voltage, concludes Barbara Pitka from the Faculty of Physics at the University of Warsaw. Okay. Moving on towards next topic. How fluctuating oxygen levels may have accelerated animal evolution. Okay. Let's see. Oxygen level in the Earth's atmosphere are likely to have fluctuated wildly 1 billion years ago, creating conditions that could have accelerated the development of early animal life. According to a new research, scientists believe atmospheric oxygen developed in the three stages, starting with what is known as the Great Oxidation event around 2 billion years ago. When oxygen first appeared in the atmosphere, the third stage around 400 million years ago. So, atmospheric oxygen rise to level that exist today. What is uncertain is what happened during the second stage in a time known as the Neopatric era, which started about 1 billion years ago and lasted for around 500 million years ago, during which a time early form of animal life emerged. The question scientists have tried to answer are: was there anything extraordinary about the changes to oxygen level in the Neopatric era that may be played a pivotal role in the early revolution early evolution of animals, did oxygen levels suddenly rise, or was there a gradual increase? Fossil traces of early animals known as Ediacaran bird or multicelled organism that required oxygen have been found in sedimentary rocks that are for 541 to 35 million years old. To try and answer the question, our research team at the University of Leeds, supported by the University of Lyon, Exeter, and UCL, used measurement of the different form of carbons or carbon isotopes found in limestone rocks, taken from shallow seas. Based on the isotope ratios of the different types of carbon found, the researchers were able to calculate photosynthesis levels that existed millions of years ago and inferred atmospheric oxygen levels. As a result of the calculation, they have been able to produce a record of oxygen levels in the atmosphere over the last 1.5 billion years, which tell us how much oxygen would have been diffusing into the oxygen to support early marine life. Dr. Alice Cross, a biogeochemical modeler who completed his PhD in the School of Earth and Environment at Leeds and was the lead scientist on the project, said the finding gave a new perspective on the way oxygen levels were changing on Earth. He added the early Earth, for the first 2 billion years of its existence, was anoxic, devoid of the atmospheric oxygen. The oxygen levels started to rise, which is known as the Great Oxidation event. Up until now, scientists had thought that after the Great Oxidation event, oxygen levels were either low and then shot up just before we see the first animal evolve, or that oxygen levels were high for many millions of years before the animals came along. But our studies show oxygen levels were far more dynamic. There was an oscillation between high and low level of oxygen for a long time before early form of animal life emerged. We are seeing periods where the oxygen environment where early environment lived would have been abductant oxygen, and then periods where it does not. Dr. Benjamin Mills, who leads the Earth Evolution Modeling Group at Leeds and supervised the project, said this periodic change in environmental conditions would have produced evolutionary pressures where some life forms may have become extinct and new ones could emerge. Dr. Mills said the oxygenated period expanded what are known as habitable spaces, parts of the oxygen where oxygen levels would have been high enough to support early animal life forms. He said it has been proposed in ecological theory that when you have a habitable space that is expanding and contracting, this can support rapid change to the diversity of biological life. When oxygen level decline, there is a severe environmental pressure on some organisms which could drive extinctions. And when the oxygen rich water expand, the new space allows the survivor to rise to ecological dominance. These expanded habitable spaces would have lasted for millions of years, giving plenty of time for ecosystem to develop. The research is published in Science Advances. Moving on towards next topic. 3D printing plant cells shows promise for shredding cell function. Hmm. A new study from Carolina State University shows a reproducible way of studying cellular communication among varied type of plant cell by bioprinting these cells via 3D printer. Learning more about how plant cells communicate with each other and with their environment is key to understanding more about plant cell function and could ultimately lead to creating better crop varieties and optimal growing environments. The researcher bioprinted cell from the model parts Arabidopsis thaliana and from soybeans to study not just whether plant cells will live after being bioprinted and for long, but also to examine how they acquired and changed their identity and function. A plant root has a lot of different cell types with specialized function, said Lisa Van Den, Brock and NC State postdoctoral research is the first author of a paper describing the work. There are also different set of genes being expressed. Some are cell specific. We wanted to know what happens after you bioprint live cells and place them into an environment that you designed. Are they alive and doing what they should be doing? The process of 3D bioprinting plant cells is mechanically similar to printing ink or plastics with a few necessary tweaks. Instead of 3D printing ink or plastic, we use bioink or living plant cells. Vandenbroek said the mechanics the same in both processes with a few notable differences. For plant cells and ultraviolet filters used to keep the environment sterile and multiple print heads rather than just one to print different bioinks simultaneously. Live plant cell without cell walls or protoplast were bioprinted along with nutrients, growth hormones, and a thickening agent called agarose, a seaweed based compound. Agarose helps provide cell strength and scaffolding similar to mortar that supports break in the walls of a building. We found that it is critical to use proper scaffolding, said Ross Sozani, professor of plant and microbiology at NC State and co-corresponding author of the paper. When you print the bioink, you need it to be liquid, but when it comes out, it need to be solid, mimicking the natural environment. Helps keep cellular signals and cues occurring as they would in soil. The research showed that more than half of the 3D bioprinted cells were viable and divided over time to form micro Cali or small colonies of cells. We expected good viability on the day the cells were bioprinted, but we had never maintained cells past a few hours after bioprinting, so we had no idea what would happen days later. When then Pro Ek said similar viability ranges are shown after manually pipetting cells, so the 3D printing process doesn't seem to do anything harmful to cells. This is manually difficult process and 3D bioprinting controls the pressure of the droplets and the speed at which the droplets are bioprinted. Sosnai said bioprinting provides better opportunity for high throughput processing and control over the architecture of the cell after bioprinting, such as layers or honeycomb shapes. The researcher also bioprinted individual cells to test whether they could regenerate or divide and multiply. The findings showed that the Arabidopsis root and shoot cells need a different combination of nutrients and scaffolding for optimal viability. Meanwhile, more than 40% of individual soybean embryonic cell remained viable 2 weeks after bioprinting and also divided over time to form microcali. This shows that 3D bioprinting can be useful to study cellular regeneration in crop plants, Sozasni said. Finally, the researchers studied the cellular identity of the bioprinter cells, Arabidopsis root cells, and embryonic soybean cells are known for higher proliferation traits and a lack of fixed identity. In other words, like animal or human stem cells, these cells can become different cell types. We found that bioprinted cells can take on the identity of stem cells. They divide and grow and express specific genes. Vandenbroek said, when you bioprint, you print a whole population of cell types. We were able to examine the gene expressed by individual cell after 3D bioprinting to understand any changes in cell identity. The researcher planned to continue the work studying cellular communication after 3D bioprinting, including at the cell single cell level. All told, this study show the powerful potential of using 3D bioprinting to identify the optimal compounds needed to support plant cell viability and communication in a controlled environment, Suzanne said. The research appeared in Science Advances. Tim Horn, assistant professor of mechanical and aerospace engineering at NC State, is a corresponding author of the paper. Okay. So I mean, the researcher of this or the people who are working on their 3D printing plant cell to promise that can be actually printed and being generated and provide each level of nutrients in the plant itself by artificially, of course. So I mean, great initiative, great man, great. Moving on to our next topic. Researcher develop atom researcher develop atom sorry researcher develop atom researcher develop auto researcher develop automatic drawing machine for making paper based meta materials. Okay. Researchers have developed an atomic drawing machine that uses a pen pencil to draw metamaterial onto paper. They demonstrated the new approach by using it make three metamaterial that can be used to manipulate the microwave region of the electromagnetic spectrum. Metamaterial are artificial engineered composite material that derive their properties from partnered microstructure rather than the chemical composition of the material themselves. The exact shape, geometry, size, orientation, and arrangement of the structure can be used to manipulate electromagnetic waves in ways that aren't possible with conventional material. Metamaterial, especially those used as observers, generally used to be thin, lightweight, wide, and strong, but but it isn't easy to create thin and lightweight devices using traditional substrate traits, said research team leader Junming Zhao from Nanjing University in China. Using paper as the substrate can help meet this requirement while also lending itself to matter surfaces that conform to a surface or that are mechanically reconfigurable. In the journal Optical Material Express, the researchers described their new technique, which uses a ballpoint pen with conductive ink to draw conductors and mechanical pencil to draw resistors and resistive films. They incorporated this process into a computer controlled drawing machine to make it more automatic accurate. Although paper based metamaterials have been made previously using inkjet printing technology, our drawing technique is lower cost, simpler, and more flexible, said Zhao. Our method could be useful for making reconfigurable antennas and meta lenses as well as metamaterial devices that absorb incident electromagnetic energy from cell phones or other sources. Automated drawing. The new drawing machine uses pens with ink containing conductive material or normal mechanical pencil with varying graphite content. It has three stepper motors, two of which control the movement of the pen or pencil in the horizontal plane, while the other lifts or drops the writing instrument in the vertical plane. The parameter of the drawing machine, such as the movement speed, are controlled by a computer. Some of the paper we tried was not very compatible with the pencil or conductive ink pens, resulting in poor conductivity of the drawn patterns, said Zhou. After some testing, we found the best performance came from using paper that is 22 millimeter thick, which is easy to obtain and very compatible with the pencil and conductive ink. The researcher used the conductive ink pen to draw patterns on paper and found the pattern to have a good conductivity of 3 into 10 to power 6 Siemens per meter. They also test a pencil with various amounts of graphite, drawing times, and drawing pressure to characterize how these factors affected electrical resistance. This allowed them to calculate the condition needed for drawing patterns with a specific resistance, creating paper metamaterials. Using their new drawing technique, the researcher designed and fabricated three different paper-based metamaterials: a polarization converter, an absorber, and conformal coding meta surface. They showed that the polarization converter could rotate linear polarization by 90 degree with a conversion efficiency of over 90% from 3.1 to 6.6 gigahertz. The absorber they fabricated had a mass of just 58.3 grams and achieved 90% observability between 2.1 gigahertz to 10.5 gigahertz. The researcher also created a conformal coding meta surface that could be used for radar cross section reduction, which is used to hide the radar signal in military aircraft and ships. This meta surface had two structural units with a 180 degree reflection phase difference to each other, which allowed them to act as 0 and 1 elements for one bit coding. When bent around when bent around a curved surface, this meta surface achieved a tenth decibel radar cross section reduction over a frequency band from 8.94 to 11.59 gigahertz. We hope that in the future we can use the drawing technology to design the and fabricate meta device that could be carried or applied to the skin to achieve electromagnetic shielding and other functions, said so. We also plan to design mechanically reconfigurable metamaterials that take advantage of the fact that paper can be bent and folded. I mean, great, man, great. Okay, moving on towards next topic. Discovery of exciton pairs could enable next gen technology. Okay. Electrical engineers from the Australian National University ANU have demonstrated how to create exciton pairs in a new type of semiconductor structure, paving the way for next generation technology required for high speed computing, information processing, and data communication. The research could lay the foundation for a new generation of smartphones and computers that are blisteringly fast but also consume significantly less energy than current devices. The new technology has been developed by sandwiching together two sheets of bendable monolayer semiconductor and allows interlayered excitons to bind together and form pairs. The research is published in Nature. An interlayered exciton is a quasi-particle made by a negatively charged electron and a positively charged hole that are sitting in two different layers. Interlayered excitons form when light is observed in a bilayer semiconductor. Interlayered exciton pair were predicted by theory decades ago, but we are the first to observe them in an experiment. Lead author Professor Yingwang Lady Liu said the discovery could help the researcher achieve a process known as superfluidity, a condition when electrical currents can travel without any loss of energy. PhD researcher Jianwen Sun said superfluidity is best visualized as a superhighway that allows excitons to travel at incredible fast speeds similar to cars traveling on a freeway. The current generation of a semiconductor technology in our smartphone and laptop limits the speeds that excitons can travel, stopping them from reaching their full potential. Mrs. Sun, who is the first author of the paper, said a good way to visualize this is the think of a car that is a bumper to bumper on a highway full of traffic. A car can only travel so fast in this condition, and the same is true for excitons. Professor Liu, who is also the chief investigator at the ARC Center of Excellence for Quantum Computation and Communication Technology, said the incredible small, lightweight, and versatile nature of this new semiconductor structure, which isn't visible to the naked eye, means it can be incorporated into into a range of miniature technologies with a promising implication for the for the space sector, quantum laser, and other quantum light sources. Professor Liu said the next challenge is to figure out a way to make the exciton superhighway function at room temperature, an essential next step to integrating the technology into our smart devices. Okay, so these are the findings, these are the study given by our scientists on the computational electronics engineering. So, yep, at the as I already previously discussed that we have started a newsletter for you guys, providing you the information that are not easily available on the surface web. So I mean, if you are interested in that kind of information, please subscribe to this newsletter. Otherwise, leave it alone. And till then, keep researching, stay curious, stay healthy. Thank you guys.